says approximately 25% of the cars sold are red, and Michael is observing cars as they drive by his house. What is the probability that he has to watch at least 3 cars go by in order to see a red one? So what we're dealing with is a scenario of probability, and we're going to review just a simple concept of what probability is. The probability can be calculated of any event, the number of favorable outcomes divided by the total number of possible outcomes. So that's what we're really working with here is a probability concept, but it's a little bit bigger than that, and that's what I'm going to try to help develop here. So the other thing I'd really want to focus on is what it means when he has to watch at least 3 cars go by in order to see a red one. So in order for this scenario to come true here, he wants to, the first car goes by, he doesn't want it to be red. He wants to wait until he gets to not the first car, not the second car, but he has to wait until at least the third car to go by, and that is the first time that we would want to see a red one. Otherwise, these cars would need to be something that is not red. So our scenario is, what is the probability that we have to wait until at least the third car? So this is where our idea is going to start. I got to wait until the third car before I see a red one. But that at least is kind of a slippery slope, because at least means I don't necessarily see it on the third. I may have to wait until I see it on the fourth car. If I wait until the fourth car, haven't I had to wait at least 3 cars before I see a red one? So you would have to figure out your probabilities for finding it on the third car and on the fourth car, and I'm just going to carry this out again. I don't necessarily see the first red car and the fourth car. I could have to wait till the 5th car before I see the red one. And here's where that probability gets more difficult to figure out, because there's not just one instance that it could be. Think about carrying this out further and further down the road. This scenario can keep going forever in all actuality. Now, it probably won't, because of the odds of us seeing a red car are 1 in 4, so we should be seeing one come along here pretty soon by the law of averages. But this calculation here is awfully difficult to calculate, so I'm going to try to present an argument here for how we are going to find the probability. So my argument starts with this. Let's find the probability of flipping a head on a coin. The probability of flipping a head on a coin, there's only one favorable outcome out of 2 outcomes, so there's a chance of 1/2. I also want to calculate what's the probability of not getting a head on this coin. Well, that in essence on this example means you get a tail, which is 1/2. So the probability of getting a head plus the probability of not getting a head is equal to 1. Okay, so that's an idea I'm trying to present here. I'm going to give you another example of this same scenario. So let's try this. I want to figure out the probability of rolling a 3 on a number cube. The probability of rolling a 3, there's only 1 3 on the surfaces out of 6 surfaces. Then I'm going to find the probability of not rolling a 3 on this number cube. And there are 5 surfaces that are not a 3 out of 6 total surfaces. But if I would add the probabilities of getting a 3 and not getting a 3, that total probability is 1. And this is the concept I'm trying to get to communicate to you. That the probability of your event happening, so I'm going to generalize here, the probability of any event happening plus the probability of your event not happening, or maybe I should do it like this, not having the event happening, almost got it, has to equal 1. So the probability of getting ahead or not getting ahead totals 1. The probability of getting a 3 on a die and a roll and not getting a roll of 3 on a die is 1. So the probability of any event happening plus the probability of your event not happening has to total 1. Now I'm going to bring that up, and I'm going to use that, and hopefully that analogy, so I'm going to slide these over, because that's kind of the scenario that we're in our current problem. What is difficult for us to figure out is what's the probability that it will happen? What's the probability that it will happen to mean? What's the probability to see the car for the first time on the third, plus the probability that he will see it for the first time on the fourth, plus the probability that he will see it on the 5th time? That one is a continuing calculation that could conceivably never end. So what I'm going to highlight here is, here's the probability that he will have to wait. This stuff up here, maybe a different color will accent a little bit better. This is the stuff that we want to happen. This is the probability that he will have to wait until at least the third car goes by. But on this side over here, this is the probability, let's grab another color here. This is the probability that he will not have to wait until the third car. So the not probability plus the will probability. So this is the event probability that our event will happen plus the probability that our event will not happen. So not E. Well, I don't know why I have so much trouble doing that one. Probability of not E together would have to equal 1. Since it's awfully difficult for us to calculate the probability of the event that we do want to have happen, let's calculate the probability that our event will not happen. And to do that, we're going to do the probability that our event will happen will equal 1 minus the probability that our event will not happen. So we do not want E to happen. Okay, so let's describe and define what happens if we do not want this event to happen. So our nots are in our first two locations in my drawing. I do not want to see a red car in this first or second spot. So what's the probability that I will not have to wait until the third car and this darn red car shows up the very first one? So what's the probability that my first car that I see is red? Well, that tells me that I got to do 1 minus. Now, the probability that my first car is red is, since there's 25% of the cars out there are red, is only a 1 in 4 chance. Okay, now remember, I'm calculating the probability that I do not have to wait until the third car. That means I saw the red car in the first car that drove by. There's only a 1 in 4 chance of that happening. So the probability, I just want to clean it up, for that first car is a 1 in 4 chance. But I also have one more chance of not waiting until the third car. I might be able to see a non-red car come by and the second car is red. Now what's the chances that the very first car, so now here's the second, I have to wait till the second car. So the first car that goes by was not red. That was a 3 in 4 chance. Then the second car that went by, this is my red one shows up on the second, that probability is 1 out of 4. This, what I'm going to highlight here, this stuff right here represents the probability that I do not have to wait until the third car. This first part here says, I saw the red car in the very first one. I did not want that to happen. My probability of that not happening was 1 in 4. The chances that I had to wait until the second car was red was the first car was not red, which was 3/4, and the second car was red, which was 1/4. So this houses all the calculations that I need. It's 1 minus 1/4 plus the chances that I had to wait till the next one is going to be 3/16. So now I got to take 1 minus 1/4 plus 3/16. So it's 1 minus, this is 16ths. It'll be 4/16 minus 3/16, which is 1 minus 1/16, and 1 minus 1/16, I don't know why I just put minus, I apologize. I'm adding these, which would be 7/16, and 1 minus 7/16 is 16/16 minus 7/16, which is 9/16. Now I know this took a long time to develop, and the reason it took a long time to develop is because we haven't had a lot of formal instruction on this, so I was trying to provide an adequate amount of background information along with how can we solve and resolve this type of question. So when you run across a situation where it's difficult to calculate all the possible probabilities when it will happen, like this one, we have to wait till the third, maybe it could be the fourth, maybe the fifth, maybe the sixth. This would be an endless stream of numbers here that we would have to add together, so it's awfully hard to determine the probability that it will happen. Then flip to the other side and calculate the probability that it will not happen, that we don't have to wait until the third car. So that would mean we saw it on the first car that drove by. That would be a 1 in 4 chance. Or the first time we saw it was on the second car, which was not a red car followed by a red car. Then we can subtract that from 1 to find our probability. So I was trying to make it as brief as possible. I apologize that it's just running long. I didn't know how to do it any other way. We may still have some discussion on this because it's a fairly sophisticated concept that we're dealing with here.